Good morning, good afternoon, everyone. I am so excited to have you joining. As people tick in, I'm just going to do a little introduction to this webinar series for those of you who haven't attended before, or as a refresher. This one is featuring Fingrid and Gridraven as their partner in deploying sensorless dynamic line ratings. But you weren't here to listen to me. You're here to learn about Fingrid and what they've been doing. And we are joined by two exceptional speakers. I've been really excited to have this. We have George at Gridraven and Marcin from Fingrid, who are going to come and talk to us.
Thank you, Anna. Thank you so much. Happy to be here, and good morning or good afternoon, everybody. From my point of view, the point of dynamic line ratings is to bring economic value and reliability value to energy markets. And so that's day-ahead markets, but also intraday markets, as well as balancing. So it's really the forecasting of ratings that's central to what we're doing so that we can use them in operational planning, as well as, of course, in the control room. And what we've seen from our projects in Estonia, where we have also full network coverage, is that there's roughly 1/3 of lines or so that cause congestion. And that depends on the network specifics. You know about your networks, how many lines have congestion, and also within each line, something like 1/3 of spans cause congestion. So that was the basic motivation for a sensorless approach for us, to be able to forecast and to cover all lines and all spans. When I was working at Estonia's national grid, at the transmission system in 2018, there was a project where we installed weather stations onto towers to compare the measurements with forecasts. And we identified that the Pearson correlation for wind was something like 0.6, which meant it wasn't usable. We left it there. There was a project with a result that we cannot use weather forecasts for ratings. Even if you know conductor parameters, you know the IEEE Segre heat balance equations, you need to have the weather inputs with a really high confidence. And numerical weather models fail in two aspects, which are critical for dynamic line ratings. One is that they give a mean value. Essentially, numerical weather predictions solve a fluid balance equation, and they give you just that value that is derived from the initial conditions that are measured by satellites and radar. So they don't give you a probability distribution. They might do ensembles, but that's a slightly different thing. Then they don't account for surface features. Numerical weather predictions at best take 1 by 1 kilometer resolution mean features, so-called surface roughness. And as a result, because they don't account with individual trees, they overestimate wind speeds by up to 2 meters per second in sheltered rights of way. And that overestimation is a safety risk if the weather prediction is used in the rating directly. So what's the solution to that? The solution is to fix those two problems, and we set up with how Gridraven solves those two problems with numerical weather predictions and makes them useful for dynamic line ratings is that we add to the weather forecast two main sources of information. One is that we have about 120,000 plus weather stations in our archive, which have multiple years of measurements, from 1 minute resolution to an hourly resolution, depends on the source. And they're all in all different types of places. Our favorite weather stations are road network stations because they have similar geographical features to rights of way. And we have to be very sure that we know exactly where the stations are, because even a 10-meter error in the coordinates can cause errors in our models. So we've gone through Google Maps to actually confirm the stations are really there. So that's one part of how we solve the issue. The other part is that for most of America and for most of Europe and Australia and New Zealand, there's publicly available 1 meter resolution 3D maps from airborne LiDAR scanning. So geological agencies fly over the country and measure where everything is. So we know where the trees are. There's an example of buildings and trees in the picture. And we also have the numerical weather prediction archives for multiple years, the operational forecast. So what we have done, we train machine learning models to learn the effect of landscape. For every weather station, we have the surroundings of that station. We know how and what features affected wind speed and direction, and also temperature and irradiation. And then we also, from those measurement histories, are able to derive the probability distributions, basically learning how and when and under what conditions weather predictions get it wrong, and fix and correct for that. And these two features of our forecast make dynamic line ratings possible. So now that we have the trained model for any region or the global version, then how we make predictions for now a specific span where there is no weather stations is that we start from the numerical weather prediction. We give the machine learning model the information about the landscape around that span, and then the machine learning model runs inference on those two data sets, and we're making a forecast for that specific span. Here's a picture of a public LiDAR from one of the California substations. It's a 3D map. It's not a picture. It's a 3D image that we feed into the machine learning, so we know the heights from the ground. This on the right is an example, and the key point here is that it's probabilistic. We allow to choose 50, 75, up to 99% confidence in the input variables for the line rating. So you have full transparency of how the rating is calculated and what were the weather conditions in that rating. And this is one span, and of course for an entire line, you will have a rating for the line. And I should also say that the weather prediction works inherently with U and V vectors. So it does both wind speed and direction, not just wind speed. And everybody's welcome to, after the webinar, go to Claude or Gridraven.com and set up your own lines. Many or most lines, at least above 100 kV, are already, the tower locations are public information and they're all there. So it should be relatively straightforward to set up a line and to obtain ratings for that already. Here on the free trial global version, there's a global weather model with, and in actual implementations, we have a more accurate local models. Right, okay, so this is actually the last slide here, and this is the summary of the solution that we built. Basically, we have fixed weather forecast in the sense that we have span level resolution accounting for the detailed terrain around that span, and we give confidence intervals to every weather input, so that when you're running the line ratings are provided based on the thermal balance equations with the conductor parameters, you are aware of the limitations of the thermal balance equations, and you know the errors in the potential conductor parameters and spans and thermal limits. Then you're able to see and verify every step of the inputs that goes into the rating, and actually have ratings that you can rely on and forecast multiple days into the future. So that's all from me. If you have questions, there's my email underneath, and looking forward to Marcin's presentation.
Okay, awesome. And also, based on one other person's presentation, I got the idea that I should probably show you where's Finland, because, you know, different continent, etc. So it's, I'm not sure, and if you can show your cursor, I'm not sure, but it's up there, up in the upper right corner. So it's next to Sweden, Norway, etc. So it's pretty much northeast from most of Europe. So it's dark, it's cold, it's, well, you know, it's one of those countries where you really don't want to assume you have 30 degrees all year round. So that's pretty much one of the reasons why you really want to have some kind of AAR DLR system here. Okay, next please. And nowadays you have this push to just, as we're getting more and more wind power plants and solar power plants, we're having close to 10 gigawatts of wind power already. Then we are not really able to physically build enough network to connect that all to our grid, because most of our wind power production is up north or on the western border, and sorry, on the western coast, and most of our production is in south. So it's hundreds of kilometers or miles that we need to transfer the electricity. And at the same time, we have a very strong push to just maximize the current grid usage, because as probably everybody has that, we just need to get more bang for a buck. And one of the ideas is that if this would even help us to just delay some investments, it would already be way more than worth its value. And in theory, it could even help us to skip some investments. Also, even up north, we are seeing more and more warmth. So last year we had 19 days in a row that were above 30 degrees centigrade, and that's the standard line rating we've been using. So we are even, it might not always give us more rating, but it should be the more correct rating. So we're also talking about the operational security here. Okay, next please. And why did we want to go with sensor solutions? So we had a pilot project a few years ago, and we had multiple sensor vendors, and we had a employee also try to create some kind of sensor system. So as Georg said, that you can't really rely on it, but it was surprisingly good on one line because we could configure it against a sensor. But of course, we don't want to install sensors on all lines to just to get our system configured. It should work without that extra parameter. But our market research showed that we should have multiple vendors available. And since this should be very cost efficient compared to using sensors on the whole grid, we went ahead with procurement. Next, please. And this is a timeline. So sure, you can get a Sybil system running in a month, but for us, it has taken us 2.5 years from the initial start to get to this point. So we did the market research. We actually managed to get the project started within 6 months, but before we got all the agreements signed for proof of concept to just actually verify what is the quality of the different systems, it had year. And we finished the procurement process last year, and in November of the last year, we took the first lines into production. And we hope to get the most of the 400 kV grid into the production probably in the next month or so. Next, please. Right, so this is the meat of the presentation. So I think most of you might be wondering, so how do you actually know that the results are decent? Because it's easy to get some results, but trying to run operations against them might prove tricky, because operations won't just take your word, because they want to be actually very confident in what they're doing. So we had 4 different validation criteria for the SAT. So I think the main one you're interested in is we took the wind forecast from Gridraven's solution, because we can put their virtual weather stations. And we have the Meteorological Institute of Finland, which has actual physical measurement stations. So we just put them in the same spot and just checked if the Gridraven solution can actually forecast that wind. So it would be fairly easy to check in different locations if we have big variations, and if we have, then what kind of variations we have. Then we also had one sensor-based system from the pilot left on one line, so we could also compare the ampacity from Gridraven's solution to that one. Then, of course, because as Georg said, their product has multiple confidence levels, so we just wanted to do a sanity check that if we choose this less confident solution, it should have higher values than the more confident one. And finally, we just wanted to make sure that if we check the wind forecast and we're certain that the Gridraven solution gives us correct values, then can we actually forecast those values? So we just wanted to check that the forecast of Gridraven solution against the real-time values. Next, please. So I'm starting with just giving you an overview on a few of those different stations. So on all these wind slides, the black one is the actual measured value from the wind forecast of the Meteorological Institution. The blue one is the confidence level at 50%. The orange one is at 90%, and the green one is at 99%. So as you can see, and let me just tell you that the line, which is roughly at the end of September, that's just our test system failing of our weekend. So that's nothing to do with Gridraven system. It was online the whole time. Sorry, Georg, it looks a bit bad. But so this is pretty much, this station is at when you're blanking at the word. So where the ships, yeah, it's a port. So that's why you have that high wind speed, because it's right on the coast. It's up north. It's it's a bay where it's windy pretty much all the time. So that's why you have wind speeds exceeding 15 meters per second, which is, I'm sorry, I can't really tell you what's that in miles per second, but it's a lot. And what you can see here is the lower the wind speed, the better the correlation with the Gridraven system. It's pretty much always on the conservative side, and where you have higher absolute errors is when it's really blowing hard. And honestly, I don't care, because if it's 6 meters per second, I can't really use bigger wind speeds than that. So the absolute error doesn't actually matter too much. What I'm interested in more is when it's blowing like 2 meters per second. And so 0.6 meters per second is 2 feet per second. So 2 meters per second is roughly 6 feet per second, or 7. So that's roughly the scale we're talking about. And this is the most windy place, and the two next slides will be showing the two different locations which are less windy. So here's the this is an airport, a bit more inland. So in the previous slide, it was mostly the maximum was 50 meters per second. Here's only 10 meters per second. Here we also see that when the wind gets very high, yes, sure, the absolute error is a bit higher, but in the lower wind speed, it's still very conservative. It catches those lulls in wind. Next, please. And here's the most interesting station, I would say, from all of those. So this was in the middle of the forest. It was actually roughly 100 meters away from one of our lines. And the maximum wind speed was only 5 meters per second. So it was very non-windy, but we still got, let's say, over 99% of the points are still on the conservative side. And here you can also see that if you put the confidence level to 99, you end up with quite a lot of 0 meters per second, because it tries to be as conservative as you want it to be. So you might actually lose some of the other values. So, you know, you gain some, you win some. And this is the real-time values. And the next few slides will be about the forecasting power. So here, I'm just saying that it's mostly, so in real time, it was pretty much always conservative. When you're talking about 24-hour forecast, it's still conservative. I'm not sure if there might be like 1 or 2 points where it isn't on point with the forecasting. And next, please. And then we tried the 60-hour forecast, which you should see. Yeah, here, yes, here you're starting to see a few points where, you know, the forecast isn't completely accurate, but still it's highly accurate, and this is 2.5 days in advance. So if you're doing wind forecasting, this should look quite good. And one more slide, please. And because, you know, we wanted to just see how far we can push it, and this is 112 hours. So this is, I think, 4.5 days. So yeah, here, yeah, you start to see some differences. But if you can actually find me some system which can forecast wind better, I would really like to hear about it. So I was quite impressed that we got this good results, because I think it looked actually better than we thought it would be. Okay, yeah, so next place. I think this is about forecasting. And then we have the green one, sorry, the blue one is Gridraven's 50% real-time values, and the orange one is the sensor values. So here we just wanted to check that the Gridraven solution is conservative compared to the sensor. And yeah, I think here you have 0 values which aren't conservative. It tracks quite nicely with the sensor. And as in the previous slide, when the values are high on the sensor, then it lags a bit behind. But, you know, I prefer to be on the conservative side, and I didn't have to invest any other equipment compared to what we have already. So this was quite nice. Next, please. And on the next slide, we'll have the 60-hour forecast. So here we have 1 or 2 points which aren't conservative, but as previously mentioned, this is 2.5 day forecast. It's still awesome. I only had to invest in 2 servers in our system, so I still like it. And so I think this is very feasible to put in use in our system. Next, please. This is going to be, okay, the next slides will be about comparing Gridraven system and different configurations. So this will need a bit more explaining to do. So this is different confidence levels and how they work. So the pink one, which is on the bottom always, that's the adjusted ambient rating. So that's just the solar and the temperature. So it does not include wind. That's why you have this daily variation. So when it's when it's sunlight, it goes down, and when it's night, it goes up, etc. And everything else on the top of it, that's the wind doing its work. And here, the idea mostly is that you can see that on quite many days on this line, we don't have that much wind, so we don't really gain anything from taking this extra risk. But for example, you have the 22nd of September roughly in the middle of the graph. There, if you actually needed that extra capacity, you could get a lot of it. So for example, if you're having some kind of outage, you could perhaps schedule like 2 days in advance. That might actually help you there. Next, please. Okay, this is going to be one of the two slides which is going to be a bit more confusing, so I'll spend a bit more time trying to explain it. And please let me know if you don't understand it. That's perfectly fine. I'm having a bit of a problem how to do that correctly. So this one is mean percentage error. So when I'm comparing the real-time values to the forecasted values, and the forecast horizon goes up to 10 days. So that's why we have 240 hours on the right-hand side. And if I just concentrate on the blue line at first, because that's going to be the clearest one. So what we can see here is the error, of course, starts from 0 because that's real-time minus real-time. And then when we get past 60 hours, that's the 2.5 days, we change the weather model. And then we get into the more higher error level. And that's just because, different models, they have different attributes. And roughly at 120 hours, we don't have anymore the wind forecast. That's why the error goes so high. So it's not that the model failed, it's just changed the base assumptions of it. And here we can just say that depending on which confidence level we choose and for which hours, it actually changes what's your expected error rating. And because of these kind of graphs, these are different for different lines. So you actually need to run the system and then choose which is the correct error or risk level for what you want to run against. Because most of them look like this. Not all of them look like this. I ran this for 70 lines, and it depends on the physical location of the line. If it's windy, if it's less windy, if it's if it runs east to west or north to south, etc. It completely depends on your physical location. So if you're taking some kind of non-sensor based system, please run the error ratings and then pick what you want to do. We are starting with the ambient adjusted rating because that's the lowest risk, and that's easy to explain to people that why we are taking it. But let's say in this case, I would be perfectly fine with taking probably the 50% confidence level up until 60 hours and then going with something like 95. It doesn't take the conductor age into account, but you can manually set it up in such a way as you want. I think we are just using the 0.9 for emissivity and absorptivity, so we just set it up like that, but you can set it conductor by conductor. Okay, next please. Yeah, so this is an example. So you could show this one and the previous slide to just see how different those two graphs are, or when you get the slides for yourself. This is why I said that they're very different. In this case, the error goes, it's interesting, let's say, but it depends completely on the line and what you're comfortable with. Yeah, I think you should have one more about the mean errors, I think. So yeah, there we go. And this is the absolute error. And here you just wanted to compare the proof of concept to the site acceptance test. And the problem with absolute errors is it depends completely on the line and what conductor you have, etc. So I personally prefer the mean percentile errors because there I can actually see, you know, how much I care about it, because it usually is below 2%, and that's usually good enough. So if you see higher errors than that, I'm starting to wonder what's going on there. But here it's 300 amps. I can't really say if it's good or bad, but then I at least have some base value from the proof of concept of when we went to the site acceptances, what I should be expecting. So let's say we have for the 50%, we have 300 amps. For the 75, we have 250 amps. And when Anna gives you the next slide, I might actually remember those two values, I hope. Here we have, we used to have the 300 amps and 250 amps. Now the 75% is less than 200 amps. And the 51 is also like between 250 and 300. So I'm guessing that Georg and the team just improved the model while we were doing the POC until we did the SAT. And here we also see that the lower the the higher the confidence level, the lower the absolute error, as we would expect. And also, you know, they're developing the system, which is nice. Do I have more slides, because I forgot? Sorry. There we go. Yeah. So about the implementation. So we started with 5 lines because that's just, you know, a very small sample, and they were all over Finland. So we got some nice geographical differentiation between the lines. And we do plan to cover pretty much all of the 400 kV grid, because it's cost efficient. And as Georg mentioned, it's hard to know where you have those bottlenecks, and especially as the grid changes, they might change as well. And what we wanted to do from the start is that we didn't want to integrate the product directly into our SCADA, because at least in Europe, we need to procure the systems every 8 years or so max. So the Gridraven's plugin is treated as just a raw DLR value provider, and we just access it via the API, and then we just put it inside our systems. We take care of all the device ratings, etc., via internal integrations, and then we just plug it where we need it. So in case we would need to ever switch it, or let's say add another product with, let's say, for 110 kV, we could just add it, and we wouldn't need to reintegrate everything. And as I mentioned, we are currently only using the ambient adjusted rating, because it's just easier to sell internally. I think as the time goes on, we will probably take some DLR into use, but I'm not sure yet when. But since we have configured it in such a way that we can pick and choose which confidence levels we want to use on which time horizon, then we can just do it that, let's say, first 60 hours we use the DLR at, let's say, 50% or 75, and then we just switch back to AAR. So I think it should be fairly easy for us to just move quite smoothly in the future towards what we actually want to use, and which would give us the most value out of the system. I think this is my last slide, so let's just try that one. Yeah, there we go. Do we have any questions? Oh, we had one question. I think I answered that, but I didn't see any other questions. Sorry if I talked too fast here also.
I think you were great. I would encourage anyone who has questions, put your hand up. I'm not seeing any yet. Clarifications, questions about how things went. Especially for those of you that are part of the affinity group, if you'd like to ask questions now, this would be your opportunity. So I see a question from Nabil. I'll repeat it. Are you using DLR data for real-time grid monitoring or for congestion forecast and market integration?
Let me rephrase that. Currently, we're just setting up the raw data. So we have plans. We have plans to use it for real-time grid monitoring. We do have plans, and we do have plans for market integration as well. So I think if we do both of those, we would probably have congestion forecast by default.
Any follow-ups? Do you want to unmute yourself and ask more, or if anyone else has questions? I see one from Swaroop. Oh, good, they're all coming in. Swaroop asks, If you see an overload in the system, do you plan to use DLR as a potential solution? Meaning, based on live forecast, if the rating of line cannot be considered or could be considered higher, indicating that it is not actually an overload.
Yeah, so the goal, I mean, this is going to be hypothetical because we haven't actually done this yet. We just have plans. So the goal would be to integrate the DLR into the day ahead model and 2 days ahead. So because we do have that's why I was focusing on forecasting. So the forecasts look quite good. So if we integrate those into the day ahead or 2 days ahead model, then we would have those forecasts, and then it wouldn't be an overload because we have the ratings updated. So yeah, we would use that as a potential solution. Though I do have one caveat that we do use the N-1, so that's the limiting factor. So we do not do usually overloads on 400 kV past the study line rating if it's just a single line because it's highly meshed system. So it just saying that it might not be the solution. It might be different than what you're using. And on the conductors,
I'll read out the
properties.
question just for the sake of the recording.
Yep.
Yeah. Could you please elaborate on how the conductor properties are considered in your model and how they affect the accuracy of the rating outcomes?
I think that's Gary because it's technical.
Sure. So we the conductor is set up span by span. So typically you might have a line with different conductors in different parts. So you set up the details of every span of the line with the conductor type, emissivity, absorptivity, and also the maximum temperature that span can tolerate. So we don't do LiDAR surveys ourselves. If you've already done LiDAR surveys and 3D line modeling, then you will have a maximum temperature value for the line. Ideally, you'll have that even span by span because you might have a span with a clearance limitation, but that's a really windy span. So even if it has a clearance, that span might have a higher rating. So these details are set up by in the system by the engineer who's implementing it.
Thank you, Jörg. Next question. Does the wind speed refer to effective wind?
I'm not sure if they're asking about how Gridraven is doing this or my comparisons. Because for my comparisons, I just used the absolute values because that was easiest for the time scale we were doing. So you could also check the direction. It's available, but it's just a bit difficult to visualize.
And I'll answer from our side that we forecast natively U and V vectors for wind speeds. And from that, we derive speed and direction. And then, of course, every span, we know the angle that the span is at. So into the thermal balance, yes, it's the effective wind speed that goes, and also the effective wind direction that goes into that.
Awesome. I see 2 more questions. I'll go to Julia first, and then Nabil, I see your hand up. Julia Selker asks, do you see value for DLR in potentially sequencing upgrades or selectively reconductoring limiting spans? Will the data be used by other teams or for other business functions?
So I'll start from the end. So the idea is that data should be used by other teams and other business functions, because one of the ideas is that we do save the raw values we get from Gridraven's product, and then we have the data which is limited by devices, and then it should be fairly easy to just do analysis where the devices are the limiting factor. So, and as we get more and more data, then hopefully other functions, let's say planning, would have some idea how different locations in our grid, how windy they are, what kind of ratings we can expect from them. Because even from the 2-month SAT, we already see that there are very different weather systems going on in different locations. So we can't really expect the whole country to look the same. Also, yeah, about potentially sequencing upgrades. Again, this is a bit of caveat. We haven't tried this, but since in this kind of product, which is sensorless, nothing is stopping you from just putting a virtual line where you are planning to build a new line. So you could actually just see, you know, what would happen and what kind of wind, etc., you would get there, and that might actually help with the planning as well. So this, yeah, so with the sequencing upgrades, that might actually help. That you can just try and see what would give you the highest yield. Selectively, yeah, and selectively reconducting, yeah, definitely, because especially as Georg said, we only did this with just putting the locations of our pylons in the system, and that's good enough. But then you have to assume that the whole, let's say, all the spans have the same rating, or you have to check that, okay, this span is 70 degrees and this is 80 degrees Celsius, centigrade, etc. But if you have the lighter day, then that would definitely be one of the options, right, Georg?
Absolutely. So yes, the dynamic ratings are calculated based on the maximum temperature in a span and conductor parameters and weather in that span. Just to follow up on those things that you just said, Marcin, that one of the things that our models are able to do is we also have multiple years of weather archives in our system. So we can run historical analyses for the past years and find which spans were limiting, in fact. So that's also something that
Nice.
other teams can use.
Had no idea.
We learn more each time we all talk. Nabil, I just unmuted you to ask your question. I see your hand up.
Yeah, thank you. And I'm sorry, I mean, I want to ask the question directly so that it's just clear. Yeah, thank you first for the presentation. And I was just actually wondering about the graph that was showing the real-time wind measurements versus the confidence levels. So one of the first ones actually that was on real-time, not the forecast one. Just for the sake of understanding, I mean, I understood that the tool is actually predicting or estimating wind in real time using the weather station data, but that is actually managing to do that, but at the span level using LiDAR and other things. So it's probably just a kind of clarification. What is the wind value that you're comparing there? Because if I understand it correctly, the tool is expected to give a span by span wind value. And I think you also have the wind, the weather provider that was providing some that information. So yeah, if you could just kind of elaborate a bit on that. I think that was the very first slide you showed. So it was showing just four graphs, measured value, confidence level 50, 90, and 99.
It's the FMI data 1/6. This one.
Yeah,
right?
exactly. Yeah.
Yeah. So the weather station in this location is roughly at 10 meters, so like 30 feet. So it corresponds quite nicely to the conductor height. And so then we could just put a virtual span there, so that the span was at the same location as the real weather station. So that would make it comparable.
Okay, so you actually put the weather station on a specific location to validate the estimation of the tool versus the measurement of the weather station.
Yeah, exactly. Because we didn't want to install weather stations on our actual lines because that's a bit difficult. So we just used the existing infrastructure in Finland to just help us with verification.
I just wanted to highlight one part, that the Gridraven's system doesn't use weather stations to make predictions. It has used 100,000 weather stations for training the model and for learning the errors and the effect of landscape, but the predictions are made purely on the basis of the numerical weather model and the landscape data around the location. So our prediction is a purely sensorless forecast for wind speed and direction.
Okay. But for real-time measurements, you take the public data provider, some from the weather provider, to take into account irradiation.
The way that the numerical weather predictions get most of the data from satellites and from Doppler radar, and they run new iterations of their numerical prediction every hour. So the real-time value, looking up to 60 minutes into the future, is based on the numerical weather prediction that has incorporated measurements from around the whole wide area for that moment, and then runs the equations forwards a bit. So there is actually no ground-based weather station in that forecast at all. It's satellite and Doppler radar that are the most data sources for the numeric weather prediction. So we take that as input and downscale it, and that's our real-time forecast.
Okay. Yeah, great. Thank you. Thank you for the clarification.
I see two more questions. I'm going to jump to David's question since we're still on a similar topic, and then back to Swaroop. But David Jacobson asks, is there a need to do calibration checks against the Finnish meteorological data every so often, like annually? Or will you be relying on DLR data without future calibration checks?
Yes, so this is actually one of the things that we need to do. So we plan to actually do Finland-wide, let's say, automatic checks. It's still in the progress. We haven't started, but because the product has the ability to add as many virtual stations as we need to, and it's fairly computation light to do that. So the goal would be to have, let's say, 100 plus stations all over Finland to just show us that if some of the DLRs at some locations are getting less reliable, then probably the lines at that region are also getting less reliable, and then we could just report that to Gridraven to fix it. Because also I forgot to say that in this case we do not get the FMA data from Gridraven. We get the Finnish Meteorological Institute data directly from Finnish Meteorological Institute, which makes it so much easier to use as verification, because we have the forecast before we get the actual data for the from the actual measurement. So yeah, we do plan to use this in the future and just expand.
David, do you want to follow up in any way? You can unmute yourself if you'd like.
Yeah, just was curious, like how often do you think you might do that? Like annual, monthly? Not sure the frequency that might be needed.
Well, well, the current system reads the data daily. So if we have just some automatic reporting set up, I think daily would be quite feasible.
Okay, thank you.
Just a follow-up on our side that, of course, we always keep 20% or so of the weather stations never in training set. So we are continually validating our forecast globally against them. So it's something also that we are doing all the time.
Fabulous. Oh my gosh. Okay. More questions coming in. This is great. I'll go back to Swaroop so I don't miss it. Back to thinking about how you use the DLR for not just real time. Yes, you plan to then use DLR baseline ratings for reliability studies and for economic dispatch unit commitment, other power system related studies. And have you already tested how these practices would be impacted for your system compared to static or AAR ratings?
Yes, so the goal is pretty much that we want to use DLR in pretty much everything where it's needed. So currently we have this real-time process running every 30 minutes to just check if we have any issues at the grid. So that's already, I mean, it's already partially fed by this. So as we take more lines into production, it's going to have more DLR lines in that system. So I just see this as being the new normal, that all the systems which are running in real time will have real-time data. For the, let's say, economic dispatch and unit commitment, etc., it's not really my field, but since the data will be available company-wide, then I don't see any problems with anyone who has the need to just grabbing it.
Thank you. All right, next question. Olu asks, how is DLR integrated into SCADA or EMS? Is the DLR output used directly for real-time dispatch? And I think you talked a little bit about the API.
Yeah, so the idea is that Gridraven is, let's say, it's in its own nice box, and it tells us stuff when we need to. So we ask it to provide new values, and then we have internal integrations up to SCADA. So it's not used directly because we want to take into account, for example, the device limits, etc., and duplex ratings and so on. So we do plan to use it in SCADA, but it's not yet used. But we do plan to plug it in there as well.
I'll follow up with this, that in the case of the Estonian transmission system, we are connected directly to SCADA, and there it was via IEC 104, and we are installed as a virtual remote terminal unit, virtual RTU, that then is a data source into SCADA. The integration was about 60 lines of code, 60. So it's relatively straightforward.
Python is fun.
It's really fabulous to know. You can tell lots of people have questions about testing and integration. I do have another question from Julia. She asks, are there plans to pair the DLR system with remote sensing of infrastructure conditions or asset health?
I would say no. I'm not working on that directly, but we do have remote sensing infrastructure in place and different pilots relating to that. So what I'm thinking, I mean, I'm not sure if this is what you're thinking, but I'm thinking like, let's see, it would be nice that if I put DLR on my line, that nothing breaks, and then you would, yeah. So I think it's a very good combo to have. I haven't talked to those people yet, at least. But I have mentioned that we will have DLR and to the device specialists, so they do know that if they're worried, they will come to me.
The questions keep coming, which I'm so glad about. Vajik asks, how do you assess the maximum operating temperature per span when you run your DLR? And do you take into account the clearance standards versus the roads and ground, etc., so that the conductor does not sag too much?
Right. So in our case, we just assume that the worst case situation for the whole grid, for the whole line. So let's say we have 60, 70, or 80 centigrade on the whole line. And if none of the span go below that, we're fine because that's what defines our clearance. But as Georg said, you could do it span by span if you have certain spans which are more critical or which are more windy.